to represent structured information. Images can be represented as screen graphs. Passages can be represented as graphs using entity typing tools to identify nodes and relationship extraction tools to infer edges. Tables have a grid-like structure, which can be represented as graphs. Similarly, complex multi-clause NLP queries can also be represented as graphs. And finally, in applications involving molecules and chemical compounds, graphs arise naturally with nodes denoting atoms and edges denoting molecular bonds. Given the widespread use of graphs across all such modalities, it is therefore essential to design some sort of a graph similarity scoring function which can mimic subjective human relevance judgments while factoring in graph structures as well as the complex node and edge features arising from various application domains. As such, a common approach is to use combinatorial surrogates, and GED is one such popular proxy. Given the combinatorial solvers are not compatible with dense node and edge features, recent focus has been on designing end-to-end trainable neural gadgets with appropriate inductive biases. Given a source graph G and a target graph G prime, GED computes the minimum cost edit path, where we are allowed a distinct set of edit operations on the source graph. In the given example, our first edit is to add a node to the source graph, followed by edge deletion from the source graph, and then two edge additions, which finally transform the source into the target graph. As listed, there are four distinct types of edits which can be composed to provide an interpretable transformation. Now, each of these four edits may incur different costs, which leads to a very versatile framework for graph similarity comparison. For example, if we allow zero insertion costs for nodes and edges, then finding an edit path with zero total cost is the same as detecting subgraph isomorphism. And such cost specifications can be guided by application domain needs. The current state of arts on neural GED prediction relies on either an early interaction modeling where cross-graph signals are transmitted during message passing, or late interaction models which process the output of the GNN modules to compute graph similarity scores. A severe shortcoming of all current models is that while combinatorial solvers support variable edit costs, all current neural models are cost agnostic, which is unable to tap into the immense versatility of GED framework. In our proposal, we address this by relying on a node alignment specification of GED. Given this example pair of graphs, we first add a padded node to make the graph sizes equal and specify an indicator to distinguish padded from the original nodes. Then the graph sizes being equal, we can now specify an injective mapping pi between the nodes of the two graphs, which is color coded. And this directly entails a set of edit operations. When the padded node D is mapped to node 2, that means a node addition is being done. There are no node deletions in this example. When an edge AC in the source graph is mapped to a non-edge 1,4 in the target graph, that implies edge deletion. And similarly, non-edges AD and DC mapped to edges 1, 2, and 2, 4 indicate edge additions. All such operations are fully described by the node mapping pi, which can also be represented using a permutation P, which in turn gives us a matricized view of the edit operations involving the node indicators of the two graphs and the corresponding adjacency matrices A and A prime. And here the ReLU is used to model asymmetric coverage cost. In this paper, our key contribution has been to design neural surrogates for these matricized operations using novel neural set divergence formulation. Our model is called GraphEDX, and given the example graph pair from before, we send the padded graphs into identical MPNN architectures, which gives us the corresponding node embedding matrices X and X prime, which are fed into permutation network to obtain a proposed node alignment map, which can directly infer the node additions and deletions. Alongside this, the node embedding matrices are further processed using MLP layers to obtain edge embedding matrices R and R prime. And the Kronecker product of the node permutation gives us the edge permutation, which together with the edge emitting matrices can be used to model the edge insertions and deletions. And thereby all four types of edit operations are distinctly modeled and can be weighted by the specified cost to predict the final GED. In our experiments, we use 7 datasets with both uniform and variable edit costs, and we compare our performance against the baselines using mean square error on the predicted GED values. We note that GraphEDX consistently outperforms all the baselines across both cost settings. Please check our paper for more details, including the design of the neural set divergence